Sì, il Burinic,
Sei quello il Burinic che sta facendo la registrazione. Non si è fatto parte niente.
Adesso sì. Corizzo, Alessandro, metti in full screen.
Veloce. Scusa, qua. Partendo. Questo posso seguire la famiglia, Burinic non so.
Sabrina, Walter, we are live, I believe.
Live?
Yes.
Yeah, okay. So
We can start.
No, we have 50 attendees.
let's wait a couple of minutes for everybody to come in. Good morning, everybody. I'm just waiting for people to slowly come in. We have about 60 people so far. Good morning, everybody. Or afternoon, depending where you are. Because okay, so let me start with a couple of words about this conference. So there are a couple of things that are unusual about this conference. I mean, we all got used to the fact to have video conferences instead of in-person conferences. And so that's not unusual. What is unusual, I see that it's 2 a.m. for some of you guys. So that's exactly the point. So what is unusual is that this conference will run over essentially 36 hours straight in 4 sessions in such a way that it will be morning and afternoon and evening for all of you at a certain point, all of us at a certain point. And so we have tried to arrange the program. Let me actually share the program in such a way that at least the keynote talks are repeated. So the first talk will be by Professor Nishimori. I will introduce him in a couple of minutes. The first talk will be live in 5 minutes and will be shown recorded at 8:15 p.m. today, local time. So this brings me to this very useful button here that you can see. You can all see on the conference program webpage. So you see, you can select your time zone here. Okay, I'm in Europe, Rome, but you can go wherever. Okay, Hong Kong, India, Libya, everywhere, Mexico, and so on and so forth. So you can change, if you change the time zone, that these times will change appropriately. So you don't have to do the conversion every time. And so this is one of the useful informations. So as you will see, for example, The first talk in the night is the one recorded in session 2 by Professor Lidar, and so on and so forth. So you can imagine the effort that the secretaries and the technical staff of ICTP have put into putting this together, and there will be people working tonight. So in case something goes wrong, please be patient. I mean, I'm confident nothing will go wrong, but just in case, remember that there will be people working in the middle of the night for you here in Trieste. So, that's more or less everything I wanted to say about what's unusual about this conference. We are in Trieste at ICTP, where this conference had to take place in person. ICTP is a Category 1 Institute of UNESCO. We are a research center, and we host a lot of activities like conferences and schools, with particular attention to our colleagues in developing countries. And we have a plethora of activities. The one in statistical mechanics, quantum computing, and condensed matter is the one I'm personally involved into. Oh, by the way, on the CMSP ICTP webpage, CMSP is Condensed Matter and Statistical Physics group webpage. This talk is, the entire conference, sorry, is transmitted live on YouTube. So if you guys have friends that want to follow this, they don't have the Zoom link, they didn't have time to register, or you want, you know, you can go on YouTube, our YouTube page, and find this. So without further ado, so my name is Antonello Scardicchio. I'm the host of one of the organizers and the host of the first of the session. The second session will be hosted by my colleague Giuseppe Santoro. And the first talk of today is by Professor Nishimori, currently located in Tokyo. Professor Nishimori needs no introduction in general in a crowd of people interested in statistical mechanics, certainly needs no introduction in a conference on adiabatic quantum computation. He is widely recognized as one of the founding fathers of this topic, which has now expanded from theory to technology, essentially. And we are very happy to have him here and talk about quantum simulation by quantum annealing. The talk by Professor Nishimori will take 45 minutes, with including some minutes for questions. So right on time, I give the word to Professor Nishimori, and we can start the talk. Thank you very much.
Okay, thank you very much for your introduction. I'm Hidetoshi Nishimori, and I'm talking from Yokohama, neighboring city of Tokyo, indeed. So my topic is quantum simulation by quantum annealing. So let me share the screen for you. So this is the title of my talk. It's on. As probably many of you know, quantum annealing was designed as one of the methods to solve combinatorial optimization problems represented in terms of the ground state of cluster Ising model. And for this purpose, we control coefficients of the transverse field Ising model appropriately to reach the ground state of the classical Ising model at the end of the process. So this was the original target, and this is the target as well, of course, now. But recently, an additional target of quantum simulation has been emerging very rapidly. And this is indeed a sort of real experiment on the chip of the annealer, the wave quantum annealer, more precisely. So this is a very exciting development, I think, because this is, in the first place, the dream of Richard Feynman to do quantum simulation on the quantum device. So let me list some of the recent examples of quantum simulation by quantum annealing. The static properties have been investigated on the spin glass problem in 3 dimensions, causeless Thalles transition in 2 dimensions, spin ice problem, the Shastly-Sutherland model, field theory, Z2 lattice gauge theory, and Griffiths-McCoy singularity. And also dynamical or non-equilibrium properties have been studied on the quantum chip, mainly in relation to the KeyboardZurich mechanism and its generalization. And I will first review 2 of the previous studies, that is the Cauchy-Thalles transition and the Shastly-Sutherland model. And after that, I will move on to explain our recent work on the KeyboardZurich mechanism, generalized one, and the Griffiths-McCoy singularity. So the first topic is the quantum simulation of the Cauchy-Thalles transition by Andrew King and co-workers, published 2 years ago in this reference. The Cauchy-Thalles transition is a topological phase transition on the 2-dimensional plane for the XY model with continuous degrees of freedom on the plane. And those authors represented this problem in terms of the frustrated Ising model on the triangular lattice, for instance, the chimera graph of the D-wave chip. And as you see in these figures, for instance, there are configurations of the Ising spins up and down, and according to the configuration of these spins, they assigned effective spins, effective cluster vectors to the plaquettes on the triangular lattice. And those arrows can point to 6 directions, which is why this model is called the Z6 model. This is a discrete model because the spins can take directions only in 6 ways, but it is known that quantum or classical thermal fluctuations can erase effectively this discreteness in some parameter range. And they studied the ground state properties of this problem by quantum simulation using quantum annealing. And one of the typical spin configurations are drawn here. Spins point in various directions, and there appear vortices and anti-vortices. And the Cauchy-Thalles phase transition is marked by the dissociation of these anti-vortex pairs. And on this phase diagram drawn on the right bottom corner, it is drawn in terms of the strength of the transverse field gamma in this direction and the temperature. And it is known by quantum simulations, classical simulations by quantum Monte Carlo, that there are phases drawn here, ordered phase, in which the discreteness of the Z6 model cannot be ignored, and the KT phase, the Cauchy-Thalles phase, in which this discreteness can be ignored, and paramagnetic phase, when the temperature of the transverse field are strong. And they traced, for instance, the system along this line on the D-wave chip. So this line clearly hits the region where the system is in the costly Thales phase. And they measured various physical quantities, including the spatial correlation function. Here's the result, the distance and the correlation function. And this line represents the power decay of the correlation function within this region, which is a hallmark of the costly Thales phase. And away from this region, for instance here, the correlation function decays exponentially. So in this sense, they successfully reproduced the costly Thales phase transition by the quantum simulation. This is a very remarkable and interesting example of quantum simulation by quantum annealing. And the next example that I will review today is the quantum simulation of the Shastly Sutherland model, recently put up on the archive by Dr. Keris and co-workers. So the Shastly Sutherland model is a classical Ising model with strong frustration on the square lattice. J1 and J2 are both antiferromagnetic interactions on the square lattice. And HZ is the field, longitudinal field. Since both interactions are antiferromagnetic, this system is frustrated, and the ground state is highly non-trivial. And they simulated this problem by quantum annealing. And this is an instance of the behavior of the magnetization, longitudinal magnetization, as a function of the longitudinal field, Hz. And it is known from theory that this magnetization has a plateau, one-third plateau, step structure in the zero temperature and thermodynamic limit. So this is a very interesting, unusual behavior of the magnetization. And the experimental results from the D-wave chip are drawn in blue here. Since the system size is finite, limited, and the temperature is low but not zero, so this sharp step-like behavior is not exactly reproduced, but there are clear indications here and there that something singular would happen in the thermodynamic zero temperature limit. This way, they identify the phase boundaries here and there and plotted those points on this phase diagram drawn in terms of the longitudinal field Hz and the ratio of the interactions J2 divided by J1. And white lines are theoretical predictions, and red crosses are the results of their quantum simulation by quantum annealing. So the agreement is quite satisfactory. So in this way, they could successfully quantum simulate the properties of this complicated problem by quantum annealing. So such studies have been emerging very quickly in recent years. And our work lies along this direction. So let me introduce the first of our studies on quantum simulation. It is about the generalized KeyboardZurich mechanism. It's about non-equilibrium, Adiabatic properties of a quantum system, quantum phase transition. And this result is published already in Physical Review Research. And this work was done in collaboration with a lot of outstanding collaborators. Bando, Susao, Shiyama, Shibata, Ozeki, Gomez-Luis, Lida, Suzuki, Del Campo. And one of the authors, indeed the first author, Yuki Bando, will give you additional information in this conference in session 3. So please listen to his talk. And this work is supported by the IAPA DARPA program. So what is the KeyboardZurich mechanism? It is quite a bit general theory, but let me focus myself on the one-dimensional transverse field Ising model to be clear and to save time. So the problem itself is very simple. It is a ferromagnetic transverse field Ising model. The state is ferromagnetic when gamma is very large compared to J. So in the limit of gamma infinity, the ground state is a superposition, equal weight superposition of all possible states into the L state. It is completely disorder. And as we decrease this ratio gamma over J very slowly, adiabatically, then the system will trace the instantaneous ground state according to the adiabatic theorem of quantum mechanics. And there's a critical point here, second order phase transition point here, gamma equal to J. And in the end of the process, when gamma reaches 0, the system is expected to reach the ground state of the trivial one-dimensional ferromagnetic Ising model, where all spins are either up or down. But if in practice, we change this parameter at finite speed or in a finite annealing time, TA. So it necessarily happens that there exist some defects or kinks which separate neighboring domains of ferromagnetic phases, this and that. So this is a non-equilibrium or diabatic effect. So the problem is to determine the number of defects n as a function of the annealing time, TA. If TA is infinity, then n would be 0. If TA is small, then n would be large. That is, n is a monotonically decreasing function we expected. And the KeyboardZurich mechanism answers this question quantitatively. Please allow me to skip the details of the derivation because of the time constraint. And the answer is written in this formula. N is the number of defects divided by the system size, the chain length in this case, defines the density of kinks, rho. And KeyboardZurich's theory predicts that rho is proportional to the annealing time, TA, to raise to the power minus d nu over 1 plus nu z, where d is the system dimension, 1 in this case, nu is the critical exponent for the divergence of the correlation length at the critical point, and z is the usual dynamical exponent. So our goal, our target is to test this prediction. And we know the concrete values of those critical exponents. First, if the system is completely isolated from the environment, there just exists the transverse field Ising model in the universe, then both exponents are known to be 1 exactly. So this exponent is 1/2, 0.5. But if the system interacts with the environment represented by the bosons here, this is the standard form of the system boson spin environment, boson spin interaction called the Caldera-Leggett model, which is maybe called bit clip error because single z appears here. Then the critical exponents change according to extensive quantum Monte Carlo simulations by Berta and co-workers. And nu is changed from 1 to 0.63, and z is changed from 1 to 1.98. And those values, those new values, don't depend upon the strength of the interaction coefficients Ck. As long as it is non-zero, those exponents stay stable. So this exponent with those values is 0.28. So we try to check which of those values are closer to the reality. And we run very extensive quantum simulations on the D-Wave machine, one at NASA Ames Research Center and another at Barnaby. And here are the results: the King density versus the annealing time in the log-log scale. Since this is a log-log plot, those straight lines mean power decay as exponent, as expected. And we excluded the data for the smallest, shortest chain L equal to 50 because the number of kinks here and there are too small and they don't satisfy the condition for the QAOA theory to be valid. That is, the number of kinks should be at least one or larger. So we extracted the exponents only from larger chains, longer chains. And the results are 0.20 for the NASA machine and 0.38 for the Barnaby machine. So these values are to be compared with the theoretical predictions. As I explained in the previous slide, the theory for isolated systems predicts that the exponent would be 0.5. On the other hand, if the spin system interacts with the bosonic environment this way, then the theoretical prediction is reduced to 0.28. And clearly, the experimental values are much closer to the case on the left-hand side. Of course, there are deviations between 0.20 and 0.28 and 0.34. But those deviations come from non-universal factors, firstly because those two values are different. Those values depend on the machine, so it's non-universal. And non-universal effects may originate in various factors, such as imperfections in the manufacturing process in each machine, or different workings of the inverse noise in each machine. But the overall impression is that the experimental results are much closer to the theoretical prediction based on this type of system under the bosonic environment. So we conclude from the experiment on the average number of things that the D-Wave chips are under the influence of the bosonic environment. So this is the first result. And we also check the distribution of the number of things because we took a very large number of data points. In the previous slide, for each data point, for instance here, we took 200,000 samples. So we have this distribution function for each annealing time, EA. And Adolfo Del Campo, one of the co-authors of this work, developed a remarkable theory which predicts this distribution function. And according to his theory, which is based on the assumption that the spins or qubits are completely isolated from the environment. And he predicted that the ratio of the second order cumulant, that is the variance, to the first order cumulant, that is the average, is a constant as a function of the annealing time TA. You saw that the average kappa 1 depends on PA in a power law. And the same is true, indeed, for kappa 2. But this ratio remains constant as a function of TA, and the constant is predicted to be 0.59. This is a very remarkable theoretical prediction by Adolfo on isolated systems in one dimension. And the ratio of kappa 3, the third order cumulant, to the first order cumulant is also predicted to be a constant 0.13. And we tested this prediction from the D-wave data. And we found very surprisingly that those data points lie on the theoretical prediction within the error bars. But we learned from the previous page on the average number of distribution, average number of kinks, that the chips, D-wave chip, is clearly D-wave qubits on D-wave chip are clearly under the influence of bosonic environment. But experiment on the distribution shows that the result, experimental finding, agrees with the theoretical prediction for the isolated system. But we don't have a theory for systems under a bosonic environment. So we expect from this experimental finding that the theoretical prediction for isolated systems should remain valid, at least to a good extent, even under bosonic environment. This prompts a theoretical development for confirmation for this part, a theory for systems under bosonic environment. And we think this is probably the first time that quantum simulation has gone ahead of theory. So this, we believe, is remarkable in this sense. And as I said in the first part of my talk, that there are several studies on the KeyboardZurich mechanism already. And I will review the recent work by Weinberg and co-workers in this reference. And they studied a two-dimensional problem instead of the one-dimensional case. And here is the result. This axis is the speed of change, which is inverse of the annealing time TA. So it's a bit confusing, but in a previous slide, we saw the axis this way. So the number of defects, this is residual energy, which is effectively equivalent to the number of defects. So the number of defects decreases as we increase the annealing time in this part, in qualitative agreement with a one-dimensional experiment. But they found a minimum for each curve, and this curve goes up again for long annealing time. And this part and this data, they analyzed by this phenomenological equation. And this first term represents this part corresponding to the KeyboardZurich mechanism. And they extracted the exponent for this part from this fit, and the result is 0.74 plus minus 0.02. And there is this theory for this two-dimensional case for a completely isolated system. And the theoretical prediction is 0.77, which is in good agreement with experimental finding. So it's a pass. In the one-dimensional case, we found that the chips, that D-wave qubits are under bosonic environment. But in two dimensions, the experiment agrees with the theoretical prediction for the isolated system. So probably, I myself think that a theory for the two-dimensional system under bosonic environment, if it is developed, would lead to a very similar value for this prediction for the isolated system, but we don't know. This again prompts the development of a new theory. And also, in the one-dimensional case, we didn't observe such a minimum for each curve. So this part should also be resolved in the future. So this is our first result. And the second is about the Grips-McCoy singularity. It is a study done in collaboration with Koji Nishimura and Helmut Katzgraber. And it will be published shortly in Physical Review A, and the print is uploaded in arXiv. This work is also supported by Adiabatic project. So I first have to explain what is the Grips-McCoy singularity. So let's go back to the Grips singularity. Grips-McCoy singularity is for the quantum system, and Griffith singularity is for the classical Ising model on the diluted lattice shown here. So consider a classical Ising model on the two-dimensional sphere lattice, ferromagnetic interactions. But let's remove some of the interactions, dilution. Then isolate clusters with their magnetic interactions remain here and there. So the transition point, ferromagnetic transition point, decreases from the value for the non-diluted system, TC star, to some value below it. And the ferromagnetic order sets in below this TC. So this part, drawn in red, is paramagnetic. But Bob Griffiths predicted almost or more than 50 years ago that the predictability chi is singular as a function of the external field H, even in this paramagnetic phase. This is a remarkable result because something is proven to be singular in the paramagnetic phase. But this singularity is very weak, an essential singularity, as shown here, as written here, so it is hard to detect experimentally or numerically. And intuitive reason for this singular behavior is relatively easy to understand. In the diluted lattice, there exist very large clusters here and there, although the probability for the existence of such large clusters is very low. The probability is very low, but they anyway exist. But since we are in the temperature range below the transition point for the pure ferromagnet without dilution, those spins in the large cluster respond very strongly to the external field. If the external field H is positive, even if it is very small, almost all spins will point to the up direction. If H is negative, even if it is very small, almost all spins will point down. So those spins for the magnetization changes almost continuously across H0. So this is the origin of this singularity, the Griffith singularity. And this is the classical theory. And it is known that quantum mechanical system with transverse field, the transverse field Ising model also has this behavior of the singular behavior of the susceptibility in this parameter range, in which case this axis becomes gamma, the strength of the transverse field. And it is remarkably observed that singularity becomes much stronger in the quantum case because quantum fluctuations enhance the singularity. And although in the classical case, the singularity is very weak, in the quantum case, the singularity is strong in the sense that the linear and nonlinear susceptibility diverge in this parameter range between gamma C and gamma C star. So we checked if we can observe this singular behavior in the basic two-dimensional diluted chimeral graph. And previously, there have been a lot of studies on this Griffith-McCoy singularity on various cases. but studies of the two-dimensional randomly diluted ferromagnet have been rare. And mostly spin glass cases with plus and minus exchange interactions have been studied. And in particular, there has been no study for the chimera graph case. And of course, there has been no study by quantum simulation on the quantum device. So we chose this structure on the chimera graph. Some of the bonds are removed from the original chimera graph here and there, here and there. So this is the regularly diluted chimera graph. But this regular dilution doesn't affect the Griffiths-McCoy singularity. Only random dilution matters. And we chose this regularly diluted chimera graph because smaller connectivity is expected to lead stronger singularities in the case of the Griffiths-McCoy singularity. And in those remaining interactions, we introduced randomness in this case. Some of the bonds are 0, removed. Some of the bonds are 1. Some of the bonds are 0.2. So we observed the nonlinear susceptibility for this system. We observed also the linear susceptibility, but it is expected that the nonlinear susceptibility would behave in a more singular manner. The singularity is stronger for the nonlinear susceptibility than in the linear susceptibility. So we mainly measure the nonlinear susceptibility on the chimera graph. And since this is a random system, the value of this nonlinear susceptibility distributes. And it is known that by nonlinear, or large value, behaves in this power law. Don't mind the notation, it is just some exponent here. And from this distribution, we can calculate the average. And you see that if this exponent b over 3z prime is smaller than or equal to 1, then this average diverges. So what to do is to measure this distribution and check the exponent here to see if this condition is satisfied in the paramagnetic phase. So the result is here. This axis represents the nonlinear susceptibility chi and the distribution in the vertical axis. And we extracted the exponent by feeding the data to some linear curve in the semilog plot, log plot, sorry. And those exponents are plotted as a function of the annealing parameter S star, which effectively represents gamma. And this is the critical point. And this part is the paramagnetic phase, and this part is the ferromagnetic phase. This is the critical point. And the exponents depend on the position in the paramagnetic phase. And those exponents, the values of the exponents depend on the way that we measure the value. But anyway, we think that the tendency is consistent, that this exponent will go below this threshold before the system reaches the critical point that is within the paramagnetic phase. We excluded the analysis, data analysis here, because the error bars are too large. Anyway, this quantum simulation has shown that nonlinear susceptibility is likely to diverge in the paramagnetic phase. This is consistent with the existence of the Griffiths-McCoy singularity on the chimera graph. And we carried out extensive quantum Monte Carlo simulations, which is classical simulation, and backed up this result. So we think we have confirmed that the Griffiths-McCoy singularity is likely to exist on the chimera graph, diluted chimera graph. So, well, time is still 35 minutes, but I can conclude. First, we simulate non-equilibrium dynamical phenomenon of the Hibilitic mechanism and its generalization on the D-wave chip. And remarkably, we believe that quantum experiment has gone ahead of the theory. That is, theory of qubits under environment should be developed to confirm the experimental finding that the ratios of the cumulant stay constant and the values are close to the theoretical prediction for the isolated system. And we also carried out quantum simulation by quantum annealing on the equilibrium or static phenomenon of the Phillips-McCoy singularity. And we found that nonlinear susceptibility is likely to diverge even in the paramagnetic phase on the diluted camera graph. And these results motivate further quantum simulations on the existing and future quantum annealers for discoveries or verifications of new and existing physics. Thank you for your attention.
Okay, thank you, Hidetoshi, for being on time for the great presentation. We have one question. By the way, let me remind you that the Q&A button where you can actually write your question is for questions regarding the talk. If you have technical questions regarding where to watch the video and so on and so forth, then you can email the secretaries. Okay, so there is one question by Nike Dattani, and it's about the simulation with the qubit with bosonic environment, and I will relate the question if you don't mind. So, how much does the exponent depend on the spectral density, ohmic, subohmic, etc., for the caldera-like bosonic environment?
Okay, the simulation by Weinberg and co-workers were done only for the ohmic case, and it is not known what will happen for the subohmic noise. So it is an interesting question. Yeah, but I don't know that.
There is another question, so let me just dismiss this. So there's another question. What about fermionic environments? I'm not sure if you can. If you can anyway.
Well, I don't know.
That they are difficult to
analyze theoretically and experimentally. Well, many people believe that bosonic environment is closer to the reality because it is harmonic. Smaller deviation from the ideal situation is represented by harmonic oscillators. But theoretically, it may be interesting to study fermionic environment, but no one knows, to be sure, to be honest. Sorry.
I do have a question actually myself, and it's regarding the nonlinear susceptibility that you spoke in. So if the exponent d over z prime becomes smaller than 0, then the probability distribution means that it's concentrated on the maximum.
Well, it cannot be smaller than 0.
Well, it cannot really be smaller than 0 because it would not be normalizable. It means that there is a maximum, right? Where the slope is now different, and everything is concentrated not around the typical value on the left, but towards a maximum value on the right. Do you observe anything like this? You said that you didn't.
Yes. In the ferromagnetic phase, we observe such behavior. The distribution becomes flat, relatively flat.
I see. So if you believe that behavior, then there must be a point at which d over z prime becomes smaller than 3.
Yes, I don't say such such a strong word. It is consistent with the assumption that d over z prime is less than 3. because the data scattering is very large around here.
Yes, yes, yes. But even if, I mean, even if you don't trust the fit, if qualitatively the slopes are in the opposite direction, then you know, something must have happened in between somehow.
Yeah, of course. Yeah.
Say if the fitting function still works somehow in the
yeah. So it is an interesting question. It is very hard to extract a good amount of data from the D-Wave chip. Quantum simulation should be done if I want to answer that question.
Okay, I find it actually quite interesting that with the noisy near-term quantum devices, you can actually get such.
Yes.
I mean, this.
Yeah, this is one of the cleanest samples. I confess. You can check other set of data on the preprint.
I will definitely. This very much interests me. Okay. Any other questions?
Okay, may I go away? Oh, there are some.
There is one. I'm just trying to understand. Randomness. No, I don't think this. Can you read it?
Yes. Can the random noise be reduced by determining randomness if there is a way to do so? Is it related to the first part of my talk, Hibilitic mechanism? Random noise be reduced.
Well, we don't have much time. If you have a very quick answer, yes. Otherwise, we'll go on.
The second question is between isolated and bosonic case. I could not understand why isolated case burdened.
No, it didn't. I'm not sure what burden means in this context. No, I mean, it gave different exponents, right? That's, but you don't have. I mean, the D-Wave chip is never isolated. It's never perfectly isolated.
It was isolated, but we knew it from intuition, but we showed it quantitatively.
Yes. So you have a theory of what that environment does, and you know it's consistent.
Well, that I don't have, but that's a very interesting path to follow in the near future.
All right. I think it's time now. So thank you very much. Thank you.
Thank you.
And so we can now go on with the next speaker, Naime Mohseni. So I will not take too much time for introduction because this is only a 5-minute talk. So and there will not be time for questions. There is a question and answer session at 10:05. So we'll go very fast on this. Sorry about that. Naime, please.
Yes.
Share the screen and show the slide.
Okay, let me to share my screen. Okay, just let me know when you have my screen, then I can start.
We can see your screen. You can go.
Okay. So, hello everyone. I'm talking from Germany. So, from Max Planck.
Yes. Sorry. I was nothing. Yeah. Go on.
Okay, from Max Planck Institute for the Science of Light, my super short talk is related to suppressing error in adiabatic quantum computing using qubit ensembles. Due to the time limitation, I try to explain our work as simple as possible. So in an adiabatic evolution, system is initially prepared in the ground state of some initial Hamiltonian, and then we gradually switch to a problem Hamiltonian, which the ground state of this problem Hamiltonian encodes the solution that we are looking for. So if the evolution, if the switch between the initial Hamiltonian and the problem Hamiltonian occurs slow enough, then based on adiabatic theorem, system always will be found in its instantaneous ground state. But if the evolution does not occur slow enough, or if system interacts with the environment, which is always the case, then system gets excited, and then at the end of the evolution, system is not anymore in its ground state, and therefore the adiabatic scheme fails. So what we would like to do is that we would like to protect the system against this kind of errors. So what we do actually is that conventional methods for suppressing error, roughly speaking, we encode the information of one single qubit redundantly on ensemble of qubits. So let's see how this kind of encoding protects the system against error. So here you can see the spectrum of eigenspectrum of a typical adiabatic Hamiltonian before encoding, and here you can see the spectrum after encoding. So let's compare them. As you can see, there is a strong similarity between two structures. However, for the encoded model, it does appear some extra energy levels, and besides, as you can see, the energy scale increases by a factor of repetition number, which here is 5. So actually, we show that this boost in the energy scale somehow guarantees that the gap between the ground state and first excited state, even in the presence of these extra energy levels, increases, or at worst case, it remains fixed. So we show some of these extra energy levels at the middle somehow are logically equivalent with the ground state, and therefore if it does happen any excitation to these extra energy levels, it does not they are not logically error. So we call this a logically equivalent state with the ground state replica state. So if this replica state appear in the vicinity of the ground state, then they somehow provide a buffer and protect the ground state and protect the system from the excitation to the higher energy levels. With actually they protect the system with a larger gap in comparison with the Bayer model. But one question that may come here is that, okay, so how we can show that these replica states appear in the vicinity of the ground state and therefore protect the system against error? That's actually one of the valuable achievements of our work, that we show there is a critical repetition number which based on any particular problem Hamiltonian, if the repetition number is higher than this critical repetition number, always this replica state appears in the vicinity of the ground state and they can protect the system. But from experimental perspective, one may ask, okay, so can we, are we able to achieve a big enough repetition number so that we guarantee that system always, the scheme always work and we can protect the system against errors? The answer is yes. Actually, our scheme can be implemented on different physical platforms, but one of the valuable proposals of our work is that we introduce a new physical platform in the context of error-suppressed adiabatic quantum computing, which has not been already demonstrated. And based on this physical platform, we can have a high repetition number, depend on whether we use gas cells or atom chips. In general, we believe that our work opens a new route towards implementing error-suppressed adiabatic quantum computing. Thank you for your attention.
Thank you, Mohseni, for the presentation and for being perfectly on time. So let's go to the next speaker, who's Glenn Bigan-Beng from University of Innsbruck in Austria. Glenn?
You hear me? Yeah, I'm about to share the screen.
Yes, please.
It says that another participant is still sharing, so give me a second. Okay.
It had to update. Okay, fantastic.
Okay. Okay. Okay.
Well, okay.
Yeah. Okay, so thank you for the opportunity to talk. In this brief presentation, I'll present some recent work on an adiabatic read-bit parity gate for quantum optimization. So first of all, let me briefly introduce the parity encoding scheme in which we have, as usual, some non-local optimization problem that we want to solve on a quantum device, and we want to know which is the optimal configuration. Then, to solve it on a quantum device which has all the local connectivity available, we can use one possible encoding is to encode the link variables into the spin variables of the quantum device. If we do this, we obtain a quantum Hamiltonian that has the advantage of having the problem variables J here encoded within local fields, but has the disadvantage of having an appearance of some constraints, which are four-body constraints on the plaquettes that are illustrated in the figure. So we can, on such a device, when we have such an architecture, we can then run usual quantum annealing. Otherwise, it is also possible to run another quantum optimization algorithm, such as the quantum approximate optimization algorithm, in which instead of performing a continuous time evolution, one applies a succession of gates to the initial state to obtain a variational state. In this case, in the parity coding, the gates necessary are 1 qubit gates, which are usually easy to obtain, and what is challenging to obtain in the general case are 4 qubit parity gates, which appear when we exponentiate the constraint part of the Hamiltonian. So then I'll discuss a possible way of implementing such gates on a Rydberg platform. So here I've written the type of gate which has to be implemented to be able to perform the quantum optimization on this architecture, and it's a gate which is essentially diagonal in the computational basis, and for even states there is an acquired phase, while for odd states there is a different acquired phase. So that is the only thing that the gate should be able to do, and we should be able to program the different phases for the even and for the odd gate and for the odd states. So the implementation we propose is based on Rydberg atom physics. So we propose an implementation where the working device is an array of Rydberg atoms, and here the plaquette on which we want to implement the gate is here designed. Is then we shine on it a laser, and the Hamiltonian which we obtain is composed by 3 pieces here illustrated. So let me just keep the details of this part of how the Hamiltonian is composed, and then go to the idea of how we use we exploit this to create the gate. So the idea is that we want to create an adiabatic gate, okay? So we want to use an adiabatic process to create the gate. We start from a case where the Rabi frequency associated with the laser is 0, and we end with a case where the Rabi frequency is still 0. If we do this and we move adiabatically, we know that the states will at the end and the beginning will be the same. So because in this case we have the states are the computational basis is eigenstate of the Hamiltonian. So the issue now is to program as we desire the phase that is acquired during this kind of evolution. So that it should be different for even and odd plaquettes. So if we do this with a 2-pulse scheme. So in the first pulse we couple the excited states of the single atoms with the laser with only one of the computational states on each atom. And in the second pulse, we do the opposite. We couple with the, let's say, now the up excited state. Okay, if we do this during each of these pulses, the state acquire a different phase, and then it may be possible to choose the pulse in such a way, the pulse shape in such a way that the acquired phase it's exactly equal to desired phi even and phi odd. So one possibility to do this, but definitely not the only one, is to use a two-pulse protocol scheme. And in this scheme, essentially, we ramp the parameters of the Hamiltonian adiabatically from one point to another, and we wait for a certain amount of time at points A and point B. So the protocol can be seen here in the figure. And the interesting thing is that for in this kind of protocol, there is an easy relation that can be derived between the waiting times you have to spend and the phase. So given a set of parameters, one can, on a phase to program, one can always find by solving an easy 2x2 linear system, which are the waiting times that has to be waited to realize exactly the 4-qubit gate we are required to obtain. So in general, this is a quite good, this gives good times for the gate, but there are some free parameters over which we can furtherly optimize to obtain faster gates possible. So the free parameters are the one which actually appear in the pulse in this pulse sequence that I described before. And by optimizing over these free parameters, we get gate times that are around microsecond with fidelities that are above 99%. So
Glenn, sorry, you are over time.
yeah, okay, this is the last slide, sorry. So in this figure, as you can see, there is the trade-off between the time necessary to perform the gate and the infidelity obtained. Yeah.
Okay. Thank you very much. Thanks. So we can go on to the next speaker, Andreas Hartmann. From the same institution.
Mm-hmm. Yeah, all right, so let me share my screen. And okay. I hope you can all see my screen. So first I want to thank the organizers for the nice and kind introduction and for the invitation. So my name is Andreas Hartmann and I'm from the University of Innsbruck. And today I will talk about efficient local counteradiabatic driving and adiabatic quantum computing. So as we all know, quantum annealing is subject to the adiabatic theorem, which poses a fundamental speed limit to any algorithm based in adiabatic quantum computation. And there have been two promising routes to detach from this adiabatic theorem. One is counteradiabatic driving, and the other one is inhomogeneous driving of a transverse field. And with today's talk, I want to introduce to you a bit the first route, namely counteradiabatic driving, as it promises a large enhancement of, for example, ground state fidelities, especially for finite speed times, which makes it really attractive for near-term quantum annealing devices. So the basic idea of counteradiabatic driving is to actually add a new degree of freedom to the system to reach a high ground state fidelity and to speed up quantum annealing in general. And so one can think of, for example, as a waiter or a waitress that transports a glass of water from point A to point B. And of course, one could stay static and walk really slowly, that is adiabatically, or we can speed up the whole system by adding a tilt to the system and to run much faster. And from a mathematical point of view, one can think of counteradiabatic driving as going to a moving frame, C tilde, by applying a unitary transformation U with respect to some sets of parameters lambda. And then if we apply Schrodinger's equation, we can actually see that the Hamiltonian in the moving frame can be described like this. So there we have a diagonal part and a non-diagonal part, which is responsible for transitions for which is responsible for transitions between eigenstates. Yeah, so our goal is actually to suppress these transitions. So that means that we can drive our annealing sweep as fast as we want without exciting any transitions. And yeah, so there are basic ideas now to actually apply such a full Hamiltonian h of t, which is our original Hamiltonian plus lambda dot times a lambda, where a lambda is the so-called adiabatic gauge potential. And so we see that if we apply this Hamiltonian to the moving frame, so here's a minus in here and a plus in here, we can cancel out these transitions. And the corresponding Hamiltonian is the one that we call the counter-adiabatic Hamiltonian. So the question is now, how does this adiabatic gauge potential A lambda look like? Or for the experimentalists among us, how do we want this adiabatic gauge potential to look like? And actually, it turns out that the exact form of this adiabatic gauge potential looks really terrible, as it requires a priori knowledge of the system's eigenstates for all times during the annealing sweeps, which is really unpractical for current experiments. So actually, a good strategy would be to just add an Hamiltonian, an extra Hamiltonian, that adds a new degree of freedom to the system. Yeah? So for example, in the case of the nearest neighbor Hamiltonian, where we have sigma x terms for the initial Hamiltonian and sigma z terms for the problem Hamiltonian that encodes our problem, we can implement an Hamiltonian that includes local sigma y terms. Okay, and then our strategy would be to find an optimal expression for these coefficients in front of sigma y by minimizing a so-called operator distance between the exact and the approximate solution. So our goal is actually to go as close to the exact solution as possible, but by applying Hamiltonian that we can actually build and implement in an experiment. And one can summarize this whole scheme or the strategy as a scheme where we actually apply quantum annealing and finding an approximate analytical solution for this coefficient alpha, and then additionally numerically vary some sets of parameters to optimize our quantum annealing scheme. And so here, if we go further, then we see, oh, actually we can find such efficient terms. So I call this, in this case, gamma. Yeah, so there can be a whole solution of a whole family of solutions like alpha, beta, gamma, lambda f. And we can do so by first give an analytical variational optimization, and secondly additionally numerical variation. And then what we actually saw is that we can even outperform with this ansatz of using just local sigma y terms. We can even outperform two-spin CD driving, which means that we would actually or additionally need to implement non-local sigma y, sigma c, sigma y, sigma x terms. And just an illustrative example can be seen here for the case of an all-to-all connected Ising spin class. So what we saw when we look at the ground state fidelities at the end of our sweep, for quantum annealing, we see that the fidelities will be really low. Then if we implement CD first order, that's the green line here, we see that the fidelities are enlarged. Then if we implement...
Andreas.
Yeah.
Sorry, you're really over time.
Okay, sorry. So actually this is already the end of my talk, so to say. So here, what we actually see that with this ansatz, we can outperform second order CD driving. Thank you very much for...
Thank you very much for your talk. We need to go to the last of the short talks by Fabio.
Hello.
Yes. Can you please share the screen?
Can everyone see my slides okay?
Yes.
So I'll get right into it. So I'm going to introduce a platform for the experimental characterization of adiabatic quantum annealing. Buttons. So I'm going to focus on a type of device that can provide this energy spectrum here, where you can see that we have two local minima in the energy spectrum during an anneal process. And I'm going to jump straight to the main result of this talk, since it's so short. effectively, if you can arrange your system to have a double local minimum in its spectrum, you can obtain the ground state of that problem much, much faster if you operate diabatically. So if you induce transitions, the idea is you go from the ground state to the first excited state here and back to the ground state via the second minimum. And if you compare this with the equivalent problem that has a single minimum, you have to actually wait, or you have to run your system a lot slower to stay in the adiabatic limit. And you see here, there's orders of magnitude speed up in this case. But I should emphasize that the examples I will present are not for computational advantage. It's just that to demonstrate that the physics enables this kind of speed up. So the problem that I'm focusing on is this 4-spin small gap gadget, as we call. So in this case, you see it's a 4-spin problem. We have 3 couplers here, and the local terms are represented, given in NG minus R. The middle qubits here are biased with this D parameter here, and the couplers are all minus R. And if you do a sort of linear schedule, so you do a conventional sort of anneal on this device, you'll find a very small local minimum. Now the question is, how do we add a second gap to sort of turn this into a DQA problem? So to do that, I will introduce some unique schedules, and here we exploit the fact that in hardware that we are using in QAOA, we can tune all of the Ising terms individually. So first, I described the transverse field, and what you see here is I effectively anneal all but one of the qubits in a traditional way, and one of the inner qubits has the X field 0 during the entire anneal. And what this does is it creates a sort of degeneracy, so you effectively have 2 ground states at this point. Now I start introducing the problem. So here I've shown all the terms but one, and this is just represented by the Hamiltonian, or the problem that I presented before. And now the unique thing about this, on top of having a HX field that is 0 during the entire anneal, is to introduce some Z field at the very beginning of the anneal. And what this does is this splits this degeneracy that I mentioned and closes it at this point here where everything crosses. And so what this results in is a extra minimum here. And of course, this is a very tunable system. So one thing we'd like to tune is the time interval between these 2 minima, which can be controlled with this D parameter, which only appears in the local fields of the inner 2 qubits. What this enables us to do is to tune the system in and out of a coherent regime. So take, for instance, we're given a system T1, which we understand as the relaxation rate from the excited state to the ground state. We can change the time interval between these minima to go in and out, within or outside of this system T1. So it could be used as a probe of coherence in a way. Another very important parameter is obviously the magnitude of the 2 local minima. So this can be controlled by making the HX field that was initially 0 non-zero. And so you now introduce a sort of unique schedule for this term. And what this does is it raises the energy of those minima. So you can arrange these to be symmetric. I showed the form of the schedule before. What this allows you to do as well, again, in the context of the coupling to the environment of the entire chip, is you can tune your system in and out of a strong and weak regime. So in conclusion, I've presented a DQA example that has 2 energy minima that are like very, very tunable. And this can be implemented experimentally, as it's a very simple system. It's hardware that we have available. And of course, we want to use this to experimentally investigate the role of coherence in DQA. Thank you.
Okay, thank you very much, Luis. So now we have really a few minutes, not 10, but 5, for questions and answers regarding these talks, if there are any. So let me remind you that there is a Q&A window where you can write your questions. Maybe some of the panelists wants to say something about, since I had to cut.
May I ask by voice, because as a panelist, the Q&A chat well, section doesn't work. Oh, someone asked. I will wait. Question. Yeah.
So there is a question. What are the couplings between the copies for Naime? This was the first of the short talks.
Oh, I don't understand completely the question. Can you clarify it?
I think the question is, you say there were copies. Your system was copied or replicated.
Yes, but our copies. The point is that in our work, the copies are coupled. It's like when I say that we redundantly encode the information, it does not mean that we generate a copy of the Hamiltonians. Actually, I didn't have time to show the Hamiltonian. We have a Hamiltonian which the copies of the Hamiltonians are coupled, which means we are not doing just some kind of classical repetition coding. So we are doing kind of error suppressing using kind of quantum suppress coding.
Okay, so there is an encoding, but it's not just a copy of the...
It's not just copy, because all the copies are somehow coupled. And that means if I want to explain it based on a physical platform, it's like that we have some ensembles, which is there is interaction between each ensemble, and also there is interaction between ensembles together.
Okay, there's another question for you from Paul Warburton. And it's, in general, how do experimental atomic approaches to adiabatic quantum computing compare with superconducting qubits?
So regarding superconducting qubit, I don't have any information, so I cannot compare it.
So you have done your on the...
But if I just want to compare it, for example, with platforms like D-Wave, so you know that in D-Wave, they need to do some kind of embedding, because what they do in D-Wave is that they do individual encoding. And what is interesting about our approach is that we do just a kind of global manipulation. So we don't need to do individual manipulation. Therefore, the repetition number is high. So if I just want to compare it with a superconductive qubit on D-Wave, I would say that we are able to prepare a higher number for the repetition code, which somehow improves the performance incredibly in comparison with D-Wave.
Okay, very good. So one of the questions that was answered by one of the speakers, actually, since the participant has been asking this question several times, let me explain why I've dismissed your question. Because the question is there any possibility of applying adiabatic gauge potential principle in unclear studies? If the studies are unclear, they're usually not presented at the conference. And I'm not sure what's the adiabatic gauge potential principles. So I will leave you to read the answer of Andreas Hartmann, who very kindly answered you. So if there are no other questions, then we can go on with the last talk. Any other? Maybe we have time for one more question, if there is any. Okay, no, this is the... Yeah. Okay, very good. So let's go now on with the last with the last talk of the day, of the session, sorry, not of the day for sure. This is the talk by Masato Motomura. The talk will last 30 minutes, and I hope we can leave some time for questions at the end of the talk, although 5 minutes will be more than sufficient since it's the last talk. Okay, so Professor Motomura, please, you can share your screen.
Okay. Can you see my screen?
Yes, we can.
Okay, so thank you very much for your kind introduction, and thanks very much also for Professor Nishimori to give me this opportunity for presenting our work. It is my pleasure to present our work on stochastic cellular automata annealing, SCA, and its non-quantum full digital annealing processor silicon chip. And it is also a kind of nervous situation for me because I'm presenting this kind of work in a totally different community. So I hope it works. Okay, let me stop. Excuse me a little bit. Okay, so let me focus on my presentation. I will first introduce motivation and describe newly proposed SCA model and static architecture, then try to discuss its implementation and evaluation. Let's start with motivation. Okay, as you know, combinatorial optimization problems ubiquitously appear in various applications, ranging from finance, logistics, drug discovery to machine learning. As such, the computation costs for solving these problems increase exponentially as the problem size increases. In that, they are quite difficult to solve, even on state-of-the-art computers. In order to overcome such bottlenecks, an alternative approach utilizing the ground state search of an Ising model is aggressively studied. Here, a combinatorial optimization problems is encoded into an Ising model, which consists of a set of up-down pseudo spins, as well as interaction weights between the two spins. Energy landscape is then derived for a given Ising system. So-called annealing processors execute a simulated cooling process to drive the Ising system into the lowest energy state, then returning the solution of the original optimization problem. So far, there have been several approaches to construct an annealing processor. These annealing processors can roughly be divided into two groups based on the Ising model structures they support. On the one hand, there is a group of sparse or locally connected annealers, such as the famous D-wave quantum annealer and the non-quantum CMOS annealer from Hitachi, Japan. While this type of architecture can operate quick due to fast and parallel spin updates, its utility for applications is generally speaking poor. On the other hand, the versatile graph structure of fully connected annealers, such as the digital annealer from Fujitsu, Japan, allows a rich variety of applications. However, its processing speed is low due to its slow serial updates. I might add here that there is no quantum solution in this fully connected category yet. Contrarily, we target an annealing processor for fully connected spins with fast parallel spin updates, that is, achieving the best of the both locally connected and fully connected worlds. In order to illustrate our target more clearly, let me outline the fundamental limitation of simulated annealing, SA. That is a conventional ground state search technique. As shown in the left panel in SA, flipping a single spin among connected spins affects the energy computation for flipping any other spins by way of the sigma-sigma interactions. For this reason, spin flip trials called Monte Carlo steps or MC steps are not independent and cannot be made simultaneously. They got to be serial, thus resulting in slow serial spin updates as depicted in this right panel. To resolve such inherently serial procedure, we need some post-SA annealing mechanism. The observation makes us establish a SCA model and statical digital chip architecture that overcome the inherent bottleneck just explained. So this slide summarizes the key contributions of this work. As a contribution C1, we have proposed a new annealing mechanism called stochastic cellular automata annealing, SCA, which realized the parallel spin updates in fully connected Ising model. Its post-SA spin dynamics achieves faster convergence toward the ground state compared to the SA on the energy landscape. C2 is statical digital hardware architecture based on SCA. It is built on the concept of near memory processing architecture. I will just briefly explain about this. And C3 is the hardware realization and evaluation of the smart hardware ideas for statical chip. I'm sorry for the noise. As for the contribution one, first I'd like to talk about key idea behind the SCA proposal. In the left panel, fully connected sigma-sigma couplings prevent parallel spin updates in conventional SA, as is already explained. As shown in the right panel, SCA spin system newly introduces spin copies, taus, for each original spin sigmas. So it's a kind of replica spin newly introduced into the Ising system. So in this new spin system, the sigmas are no longer dependent, no longer coupled to each other. In a similar manner, the taus are not coupled with each other. Instead, the couplings are all from sigma to tau. They are redirected intra-sigma from sigma to taus. So by treating these taus to represent spins after the update and sigmas to represent spins before the update, respectively, we can establish new SCA spin update mechanism. So let me go into a little bit more detail. The upper panel includes Hamiltonian of the fully connected Ising spin system, whose total energy is determined by all sigma states. On the other hand, the proposed SCA spin system, Hamiltonian, is extended as shown in the lower panel. Here, we introduce tau instead of sigma in these two terms. As I presented in the previous slide, this Hamiltonian does not have sigma-sigma couplings, as well as tau-tau couplings. So we can update sigma to tau without considering the effect of other sigmas update. To realize this parallel spin update, an additional term written in this red color is introduced in the SCA Hamiltonian. This term increases the total energy when the state of the taus, tau x, is different from sigma x. The SCA Hamiltonian becomes equivalent to the original Ising Hamiltonian when this term becomes zero. That is, when there are no sigma flip from sigma to tau. The Q, called pinning parameter, represents the strength of restricting spin flips. And in SCA, we need to control this Q appropriately, as we will see later. Let me remind you, this type of extended Hamiltonian was originally introduced by this reference paper, where it was called Probabilistic Cell Automata, PCA. They used this PCA model, quite similar to this one, for sampling, whereas here in this work, we propose to use this extended spin system for annealing, that is SCA. So mathematicians in our group have studied the properties and annealing behaviors of this SCA. The first panel shows that the SCA Hamiltonian is simply equivalent to the Ising Hamiltonian when there is no spin flip, that is sigma equal tau. The second panel shows that the equilibrium distribution of SCA is nearly equal to the Gibbs distribution by defining the SCA transition probability as shown here, and then increasing Q to infinite. I'm not going into the detailed description of mathematics behind this, but you can refer to this archive paper, which is describe more about SCA mathematics. By the way, since this transition probability expressed as the product form, which indicates that all spins can be updated independently and simultaneously. However, since large Q restricts spin flips significantly, because this is the pinning parameter, using too large Q in the kneading process may lead to a very slow convergence. The third panel shows a countermeasure for this issue. It claims that SA and SCA reach the same ground state when Q is greater than the half of the largest eigenvalue of -J, as written here, and temperature is reduced towards 0 in a logarithmic manner. So this is what mathematicians have proved. Details, as I mentioned, details will be described. Details are described in this archive paper. Okay, as is depicted again in the left panel in this slide, SA dynamics updates single spin in one MC step, then sweep across all the spins in serial manner. In the right panel, SCA dynamics allows for simultaneously performing spin updates for all the spins in one MC step. This is all parallel process for spin updates. Here, again, sigmas are simultaneously updated to taus in one MC step, and then the tau becomes the next sigmas in the next MC step. Conventional SA features serial process, which means slow, whereas the proposed SCA features parallel process, which is substantially faster, as we will see later. So, I covered what is basically SCA. So I will going to cover the hardware architecture for implementing SCA for the contribution too. The left panel summarizes SCA spin update mechanism again. To obtain the updated spin state tau from sigma, the current spin state sigma and its interaction weight must be remembered. Here, the spin states and interaction weights are, these are the information, and spin update process is some hardware operation. Therefore, we developed a new memory architecture that is a kind of the computer architecture term that places constant interactions in the wait memory, which is static memory, and places update logic. This is a kind of a gate logic, very close to the memory. These weights are read out from the memory parallel manner and then are processed in parallel by the spin update logics. The spin states are frequently updated so that they are stored in registers not in memory. We named this architecture for SCA as Statica. Spin updates in this static architecture are realized by the following two processes, basically. The first process is local field accumulation. Calculate this multiplication and summation. In this process, the products of spin values and weights connected to a given spin, here in this diagram, are accumulated. Then each spin is updated in parallel according to a probability P, threshold L in the second process. I have two detailed slides of the hardware mechanisms and architecture regarding this static architecture, but I think it's a little bit too much for this occasion, so I am going to skip. But anyway, we have built up some smart hardware mechanism for doing the parallel and efficient spin updates using memories and logics. So just here, two slides. If interested, I can cover it later. Okay, now I'd like to present the implementation and evaluation results. So here you see some photo of the Statica chip that we have developed. This is just a plain LSI silicon chip, which work at the room temperature. Which have memories and logics, as I already explained. If someone is interested, it has been fabricated in 65 nanometer CMOS process, and it runs like 300 megahertz, and the operation power is less than 1 watt, or something like that. And the number of spins that this small chip, by the way, it's 3 by 4 millimeter square. The number of spins integrated in this chip is 512. It's not too much big, but they are fully connected between each other. And also the interaction weights, the precision of the interaction weights among the spins are 5 bits. So let me compare our proposed SCA and SA in some basic characteristics. So these two chart compares SA and SCA. Left one is for 512 spins. That is maximum Statica chip capacity. That's showing measured SCA data. While the right one is for 2000 spins. That's showing simulated SCA data for comparison. By the way, the graph shows max cut benchmark, which features a fully connected interaction among spins. So it's good to see the data for the comparison. So both results for the 512 and 2000 show that SCA, this blue line, converges n times faster than SA, n equals to the number of spins. So all parallel spin updates are actually working here for speeding up the process, spin update process, like n times faster than conventional simulated annealing. The next graph explains the advantage of our spin update mechanisms that I think I've skipped. So I'm going to briefly explain this view graph also. So left diagram shows the number of flipped spin in one MC step. Here MC step again try to flip all the spins in the system. So earlier in the MC step, you are seeing a large number of spins are flipping, but later in the process, only a limited number of spins are flipping here. And all I can tell here on the right diagram is that we are utilizing this feature, decreasing number of actual spin flips for speeding up the hardware operation. Okay, the next slide summarizes the comparison with existing fully connected annealing solutions. The left histogram shows the accuracy and processing speed for a MaxCut benchmark K2000, and the right-hand side summarizes the system specs. The cut values of MaxCut is equal to its score, so higher the graph, the better. The comparison shows that Statica, this blue one, outperforms other solutions in processing speed and accuracy. Other solutions are SP for simulated bifurcation, which was proposed from Toshiba, SIM coherent easing machine, which was proposed by NTT using optical fibers, and traditional SA, simulated annealing on CPU. So our proposal is much faster, much more energy efficient, and also accuracy-wise better compared to other solutions in this chart. Okay, so I have to say that we had planned to compare this Statica and SCA approach with a D-Wave machine, but so far, difference of underlying easing model that is fully connected and locally connected have made it difficult to compare in an apple-to-apple manner. That is because, as is well known, minor embedding process severely degrades actual performance of sparsely connected machines for realistic applications. Okay, I'm approaching the conclusion. In conclusion, the Statica, the chip we have developed based on SCA proposal, solves fully connected optimization problems for fully connected spins with parallel spin updates with following these key achievements: post SA type SCA annealing achieves n times faster conversion, SA based near memory hardware architecture, Statica, and Statica have outperformed all the existing solutions. We have demonstrated the Statica chip in this International Solid State Circuit Conference earlier this year, February, where 22 queen n queen problem is mapped on this Statica chip and solved in real time. This is the demonstration setup. So we just need a small board and a laptop PC for doing this type of demonstration. Okay, so this is the final slide. So it's a kind of postscript. The conference that we have conducted the demonstration is a kind of flagship conference in integrated circuits, and attendees there belong to quite different research community from this type of content conference. So a bit funny situation there were that visitors to the demo all asked us why it is not cooled, how quantum bits are fully connected, etc. So in their mind, annealing machines is something like D-Wave machine. So we ended up posting a panel like this for clarification. So basically saying it is not a quantum machine. So it does not imitate quantum computers or quantum annealers either. It is not using any magnetic spins. It's not physically cooled or annealed. So what Statica is plain CMOS digital chip. It simulates classical easing model, use bits and SRAM, all the old techniques. Okay, so this concludes my talk. Thank you very much for the kind attention. Here are the references.
Thank you very much, Professor Motomura. So there is a question by Viv Kendon regarding comparison graphs. If you can show again the slide where you compare the different results between Statica and the other hardware.
Sorry, let me.
Can you share your screen again?
Sorry, wait a minute, please. You're having a trouble showing the. Oops.
So maybe, I mean, maybe you can answer this question without resorting to the.
Yeah.
So the question is, do you have? So the y-axis was different for Statica, so it was hard to see. It was really better. If you have numbers to show this more clearly. Yes.
Okay, sorry. Now you're seeing.
Yeah, this one. Yes, no, that one. The
Okay.
one with this.
The question again, please.
So the question is regarding the comparison between the different hardwares. So I think the reference is to the slide with the histograms.
Oh, I see.
Further down. Yes, this one. So it says the y-axis is different. And so, but this is because it's the
it's
less
kind of graph. Yeah. So we did the trial repeated times. The distribution solution is different. So there is a little bit difference, but basically we did the same.
And what about the power consumption numbers for the other two hardwares, the yellow and green one?
Yellow. Oh, I see. So this is the large system using optical fibers, long optical fibers. So although we tried to understand the power, but we could not get the correct number. And the green line is just running a program on CPU. So it's like several tens of watts or something like that. So it depends on the system. So we didn't put that number.
Can I ask a more mundane question? How much does the Statica chip cost if one wanted to buy? Is it in production?
So it's an experimental chip. So this chip itself is very costly because of all the other R&D cost. But generally speaking, the chip like this is like it's like several dollars.
$100 or so.
Quite less than that. So just $4 or $5 or something.
Oh, you
like
mean
that.
the production cost would be
production wise.
I see. Okay.
The question is how much R&D you spend on this, right?
I have a question actually. So you have used it on the fully connected system, but can you just turn off the couplings between embedding a lower connectivity into a fully connected one?
Yes.
Simulate something which is, I don't know, like 3D?
Yeah, that is a very nice question. So we have 5 bits for the connections. So basically putting 0 to the interactions, basically they are unconnected. So that's a baseline. So our future plan is to do it more wisely, like embedding. When you embed a smaller program, then you can get extra efficiency by not calculating unnecessary connections.
Okay. Because, I mean, the issue is that, I mean, at least if you look at mean field theory for spin glasses, I mean, the higher dimension one should behave like fully connected in some sense. So probably an algorithm that works fine on the fully connected spin glass would work better on, I don't know, like 4-dimensional, 5-dimensional using spin glass than an algorithm like, which is a local one in some sense. So I was wondering whether you were thinking of going in this direction.
Yeah, so higher dimensional interconnection among spins will be our future challenge. So I guess we have worked on the parallel updates of spin to spin simple interactions. So next natural step will be naturally the higher orders interactions.
There is another question. I will allow it because of time. So it says, how much time approximately will it use Statica to solve the game of chess? So I think this was related to your queen problem, right? So it's not the game of chess. It's a different problem.
Oh, n queen?
N board, and you have to put n queens in such a way no queen can attack any other queen. So it's not the game of chess. I mean, I don't think the one, as the use this chip to solve a game of chess like we know it, but it's the N queen problem, which is
kind of famous toy program for combinatorial optimization problems.
So how long does it take to solve the n equal 22?
This N queen problem?
Yeah.
Okay, I have an additional slide here. SC on Statica chip, 56 microsecond, 600 milliwatt. And SS software Python on this the laptop, 2.5 sec. Yeah, you can see these numbers.
All right. Okay, thank you very much. So I will thank you and close here both your talk and the morning session 1, morning in Trieste. So let me remind you that the session 2 starts at 6 p.m. Trieste time. And let me remind you again that you can change your time zone in the program. Let me share the screen again just to, what is it here? Here you can look at the thing here and change the time zone to your location, whatever that is around the world. And that session 2 will start at 6 p.m. Trieste time with the moderator, my colleague Giuseppe Santoro from SISA, co-organizer of this conference. And the talk by Professor Nishimori will be reproposed at 8:15 p.m. Trieste time again. So I thank you all the speakers. Thanks to all the speakers of the morning and all the panelists and for the questions and discussions. And I leave you here and I will see you at 6 p.m. for session 2. Goodbye.
Thank you.
Thank you.